Yeah, hello students. So in this lecture, we'll be looking at different types of adders, and we'll be starting with RCA. The first type of adders that we'll be looking at is RCA. So RCA stands for ripple carry adders. Okay, so these are nothing but the adders. Uh, if we write the circuit of addition, the process of addition. Uh, uh, or let me explain this with the help of an example. Suppose you have two 4-bit numbers A and B. Suppose A is 1010 and B is 0110, and you are doing this addition. Okay, so how do we start the addition? Using pen and paper. Okay, we take these two numbers. What do? We go with the rightmost set of bits. Okay, and we add these two. So that is 0 plus 0 is 0. Okay, and then we go to the next set of numbers, that is 1 plus 1. 1 plus 1 is 2. 2 in binary is 1 0. So 0 goes here and 1 goes as a carry to the next stage. Now we add these three bits. Okay, so that is 1 plus 0 plus 1 is nothing but 2. 2 is again 0, 1. Here again 1 plus 1 is 2. That is nothing but 0 and 1 over here. So this is how we perform addition using pen and paper. If you mimic the same process that we have done over here into hardware, okay, so whatever you have done using pen and paper, if you mimic the same in hardware, whatever adder you get is nothing but the ripple carry adder or the RCA. Okay, right. So ripple carry adder, the structure of ripple carry adder is something like this. Okay, right. So this is a full adder. We know full adder can add up to 3 bits. Okay, so this is A naught, B naught, and C naught. So this full adder completes the addition of your first stage of or the first set of bits, that is these two, the rightmost bits. Okay, and then this is the sum bit. Okay, sum bit is nothing but this one. Okay, and the carry generated by the first full adder is propagated to the second stage. Okay, so like in the second stage, if you see 1 plus 1, you got 0 and 1 as carry, which is given to the next stage. The same thing is happening. If there is any carry generated in this first stage, it is given as carry to the next stage. Okay, so whatever you do using pen and paper, if you replicate it in terms of hardware, what you get is nothing but a ripple carry adder. Here you can see there are 0 to n minus 1 full adders connected in this fashion. Okay, the name ripple carry adder stems from the fact that the carry has to ripple through the entire stages. Okay, if you see, so this particular full adder has to wait for the carry from this full adder. Okay, and this particular full adder has to wait for the carries from these two stages, and so on. At this particular nth stage, this full adder has to wait for the carry from the n minus 1 stages. Okay, so that is the carry that is coming rippling through the previous stages. Okay, so that is why this is called the ripple carry adder. Okay, so and one problem with the ripple carry adder is it results in glitching. Okay, what is a glitch? Glitch is nothing but a momentary, okay, which is nothing but a momentary wrong value. Okay, we don't want wrong values, but sometimes the result is momentarily wrong. Okay, momentary wrong value is nothing but a uh, glitch. Okay, so this can be understood with the help of an example. Suppose I am adding two numbers. Let me color code these. Suppose I am adding a, let me take a simpler example. Suppose a is 000 and b is 0001. Suppose I am adding these. Now I would like to draw the ripple carry adder for this. Okay, so this is nothing but a full adder. So this is a 4-bit ripple carry adder that I need in order to perform the addition of two 4-bit numbers. Here the two 4-bit numbers that I am using are A and B. Okay, so let me label these as well. So this is A naught, A1, A2, A3. So this is nothing but B0, B1, B2 and B3. So the result is 0 plus 1 is 1. There is no carry. 0 plus 0 is 0, 0 and 0. So this is nothing but your S0, S1. So this bit is your S2 and this bit is your S3. Okay. So if you see, there is no carry as such in this stage. Okay. So let me finish this. So, so let this be A3, A2, A1, A0. Okay. So B, for B I'll be using the red color, B3, B2, B1 and B0. So let me put the B's here. 0, 0, 0, 1. A is nothing but all zeros. 0, 0, 0, 0. Okay, right. Now we get S naught here, which is nothing but equal to 1. And of course, C in this case is 0. Okay, there is no carry. Carry is not there or not at all required for the first stage. Okay, right. So the carry generated by this, okay, let me call it C1. C1 is 0. Okay, so C2 is also 0 and C3, this is also equal to 0, and the final carry out, there is no carry out as well, it is also equal to 0. Okay, and these are nothing but S1, S2 and S3. So S1 is 0, S2 is 0 and S3 is 0. Okay, now this is how the addition happens. Now let me try to explain you the process or the phenomenon of glitching, how glitching occurs. Now if the one of the operands changes, okay, let me say now, let me follow the same color coding. Okay, let me now say if A is equal to 1111 and okay, let me follow the color coding. So let me say B is equal to 0001. Okay, so suppose this is the time axis. Okay, so this is the time axis. So say at t is equal to -1. Okay, so these are the operands that I'm applying to my ripple carry adder. And at t is equal to 0 seconds, these are the operands that I'm giving to the ripple carry adder. Okay, so let me draw the diagram again. Okay, so since I am doing the addition, 4-bit addition using ripple carry adder, I have the 4 full adders. Okay, so this is full adder, full adder, full adder and full adder. Okay, of course I'll color code the operands. Okay, A3, A2, A1 and A0. I'll color code the operand B with red. So B3, B2, B1 and B0. So at t is equal to -1 second, my operand A was all zeros, but now at t is equal to 0 second, my operand A is all ones. So what happened to the blue lines here? Okay, it is all ones. 1 1 1 1. Okay, so but let me finish this addition first. This is 1 plus 1 is 2, which is nothing but 0 1. 1 plus 1 is 2, 0 1. 1 plus 1 is 2, so 0 1. 1 plus 1 is 2, so 0, and we have a final carry out as well. Okay, right. So in this case also the input scene is equal to 0. Okay, so at t is equal to 0 seconds, what happens the moment that we uh, so let me draw b as well. So this is nothing but 0 0 0 1. Okay, so at t is equal to 0 seconds, as soon as I apply a is equal to 111, from a is equal to all 4 zeros, now I am applying a is equal to 111. Okay, so what happens here is, so this stage, only this stage, the first full adder, only the first full adder would have computed its carry computation. So we know that 1 plus 1 is 2, 2 in binary is 2 in binary is 1 0. So 0 goes as the sum bit here, s naught is 0. Okay, but here the carry is of course 1. But what about these carries? These carries are not yet calculated because at t is equal to 0 seconds, only this particular operation took place. Okay. Only once this carry is given to this full adder at t is equal to 1 seconds, this full adder, the second full adder, will complete its addition process. At t is equal to 0 seconds, of course, it is not getting this input as 1. But what is the output of this full adder? It will be nothing but the previous output. The previous output is 0 here. Okay, and the previous output of this full adder is 0 here, and the previous output of this full adder is 0 here. Okay, so what happens here? So here s1 is 0. Okay, so s2 is also equal to 0, or rather, sorry, here S1 will be 1 plus 0, which will be equal to 1. Okay, at t is equal to 0 seconds. Remember, this carry this carry 1 that is generated by this first full adder is not yet seen by this. Okay, right? So this full adder will now see only 1 0. Okay, so s2 will also be equal to 1, and similarly the final full adder will also see only these two, 1 plus 0. So s3 will also be equal to 1. But what is the final result? Final result is a 5-bit number, 1 and 4 zeros, 1 0 0 0 0. But what are we getting? 0 1 1 1 0. Okay, so which is a wrong result, which is nothing but a glitch. Okay, so now you get the idea. So what happens at t is equal to 1 second is, okay, so this full adder will also now complete its addition operation, and it will generate this carry. At t is equal to 2 seconds, this full adder will then finish the addition operation and will generate carry, and at t is equal to 4 seconds, this full adder will generate the will finish its addition and will generate the sum and carry, and then finally the output. Okay, so if you see, all sums are wrongly computed to be 111 here, but their actual values are supposed to be 0. Okay, so this is nothing but a glitch, where I defined a glitch as a momentary wrong value. Okay, so this S3 will be corrected after 4 seconds, S2 will be corrected after 3 seconds, S1 will be corrected after 1 second, and S0 is the only value that we have without any glitch, and all other S3, S2, S1 suffer with glitches. Okay, so this is the disadvantage of ripple carry adder. Okay, what is the major disadvantage of ripple carry adder? So ripple carry adder suffers from glitches. Okay, and its complexity is linear. Okay, suppose we are doing addition of two 4-bit numbers. Suppose we are doing addition of two 8-bit numbers. How many full adders do we have? So we have 8 such full adders. Okay, and you know the glitching actually increases as the bit size increases. Okay, so if we have a 16-bit full adder, 16-bit operands to be added, a and b are two 16-bit numbers. We need 16 full adders in this configuration, and you know the glitching will be even more. Okay, so this is about the ripple carry adder.